reading broadcast. Okay, looks fine. Okay, so yeah, this time we go over. Okay, so as a review, we go over a lot of things, mostly the properties of a system, and two of the property we focus on linear and time invariant. And we show that linear time invariant systems have very nice properties, such that you can totally characterize them by this h function h of n. And yeah, you can totally characterize any LTI system by its unit impulse response h. And h is defined as, once again here, h is h naught, which is the response of the system when you have the input as the unit impulse. So the delta function for discrete time case. So we focus on discrete time case this time. For discrete time case, this delta of n is 1 at n equal to 0 and 0 everywhere. So put that as your input to your system, and you have some response. That's your unit impulse. And we say that because your system is linear, you can decompose whatever input as sum of a lot of different input impulses, like sum of x at different time step k, and all those shifted unit impulse delta of n minus k. And you will have the corresponding then your output will be the same linear combination of the responses to those delta. Then if the system is also time invariant, then all those h sub k, which are the response to delta of n minus k, should all be the time shift of delta of should all be a time shift of h naught, because delta of n minus k is time shift of delta of n. Then h sub k should be the time shift of h sub 0. Okay, that's why we get this. So if it's time invariant, then delta of n minus k go to h of n minus k. Then we see that y of n can be just represented by h this summation k x of k, which is something dependent on x, and this h of n minus k. So this x depends on your input, so the only thing dependent on your system is this h of n minus k, and that depends on this h of n function. So your system is determined by this h function. And we will also like to write this whole summation thing, so we call this a convolution. It's a way to compute one function from two functions. So we write it like this way: x of n and this star, then h of n. So that's a convolution between x of n and h of n. And that will be a function of n once again, and it's our output y of n. And if we are good on our schedule, we'll see more property of this convolution operation. Okay. And then yeah, then we go through more detailed example of convolution. We see there are two ways to see convolution. The first one is like how we derive convolution. We see this as your y of n is the summation of different component to the different response. So h of n and shifted to different time, and you sum together. And there are another way to see this is you can fix an n and plot your x of k and h of n minus k with respect to k. Okay, so it's important you are plotting with respect to k. Then h of k will just look at x of n, because you are just changing a variable name. Excuse me. You are just changing a variable name from n to k. So you have x of k here. Then you need to think about what's your h of n minus k plot against k. And so what's happening basically here? So you take your h of n, then you take the time reversal. So you go to h of k, but this is h minus k. So you take time reversal, so you flip back and right. Then what this plus n do is you will pull your h of minus k to the right by n step. So if n is negative, then you should push your this h of minus k to the left by whatever negative amount, and as n increase, you pull this to the right one step by one step. And then you look at your x of k and h of n minus k, and you multiply them together as this equation requires. So you multiply at each k together. So usually they will cut off somewhere, so you can look at the region that actually overlap. So you multiply them together, then you sum over the multiplied result over all the k. And that's how you can calculate that for different n. Okay. So it's very confusing between k and n, but you remember you are plotting against k here, and you are pulling this h through as your n increase, and for each n you will get one number, and that's your y of n. Okay. And we see that we would like to separate it into different regions. So you have x look at this, and h look at this, go to infinity. Then you flip h, look at this, then you try to see how they overlap with different n. And usually for some n, they will have no overlap, so you see the answer is 0. So here for negative n, you see this thing and this thing has no overlap. So the convolution for n less than 0 is 0, and when you increase your n, so you pull this to the right more, and this thing and this thing has some overlap in this part. And then you need to actually do calculation to so you plug in the formula and do calculation and see how much y of n is actually is, and your answer should be in different parts. Okay, and here we're a more complicated example. So this is a very complicated example where both x and h has two boundaries. So x is cut off at 0, cut off at 4, and h is cut off 0, cut off at 6. So when we do the thing we want to do, we have a lot of boundary. So we flip. So as we said, we do time reversal, so flip the h left and right, and so it should look like this, something like this, and we start from negative n. Negative n. So we see negative n, we can see that there is no overlap. So the convolution, we multiply together, is just 0, so it should be 0. Then when we have n between 0 and 4, so it has a partial overlap between x and h of n minus k, x of k and h of n minus k. Then you see the overlap is whatever from 0 to n here, and you can sum them together, and here we usually put this geometric series so the summation is easier. So you can sum this from 0 to n, and then you plug in the formula, you get this result. Then you see you pull this h of minus k more. Now they have 4 overlap between 0 and 4. And so you sum from 0 and 4 this, and you get some result. And finally, we have this n minus k, so this n minus 6 part is between 0 and 4, so once again we have partial overlap between n minus 6 and 4, then we get this result. Then finally, when we have very large n, so when n minus 4 is bigger than 4, sorry, n minus 6 is bigger than 4, that means n needs to be bigger than 10. Then once again, this and this has no overlap, so multiplying together is 0, so everything is 0. Okay. So yeah, so in this very complicated example, your answer is put into 5 parts. And I have something, so I guess a bit different, but so if you want to brute force this with just algebraic calculation, although you still need to kind of do the interval analysis. So you can also say your h of n is, so if you want to write down this interval, you can say it's alpha to the n. And if you want to describe this interval of n between 0 and 6, you can say you multiply by u of n, so that will cut off anything less than n less than 0. And then you subtract another, you subtract all u of n minus 7, so that will cut off everything that's n bigger than 6. Right? Then yeah, so this h of n will describe this h in different interval. Then you can put in the summation. You can put in the convolution summation. So your x of n is easier. Sorry, h of k is easier. So x of k will just we can also do things like this u and u, but because x of k is very simple, it will just cut off your k between 0 and 4. So x of k, we can just say it makes k sum from 0 to 4. Then we have our h of n minus k here. So this alpha n become alpha of n minus k, and all those u of n become u of n minus k, etc. And here, once again, you need to be careful. You are summing over k. So summing over k, and so things don't depend on k, we can just pick them out. So this alpha to the n, we can get out as alpha to n. Then we have this summation alpha to minus k, alpha to the minus k, and the difference between those unit step function, and also have this k from 0 to 4. And we can solve this unit step function to see what they actually say. So we want n minus k bigger than 0. That means k is less than n, and this means okay, so this is reverse. But anyway, and the second u means that n minus k minus 7 is bigger than 0, means k is less than n minus 7. So we see the difference between those u give you a region of k is between k is less than n, and k is actually bigger than n minus 7. So the only possible k is between 0 and 4, and n minus 7 and n. And now you still need to analyze the case. So how does this interval overlap with this interval? And you need to shift n around to see. Okay. And yeah, so that's just a little more algebraic way, but it's basically the same analysis of we try to pull the h through and see the different results. Okay. So any question about this very complicated example? No? Then we'll actually see a little easier example. Okay. So those are examples. So it's basically the same thing, but now the x is a 1 with 2 to the n, but x and h are basically the same as we'll see maybe today. Anyway, so now x is the 1 with exponential, and h of n is a unit step function. And both of them, so they all go to infinite, so actually makes things a little easier because both of them all have one boundary now. So x of n is cut off at n is 0, because you have this u of minus n here, so n need to be less or equal to 0. And we have this 2 to n, which is exponential growing, but our n is negative, so it's an exponential decay to negative n. And we have h of n is our unit step function. So once again, do our thing. So we have u of minus k will flip around, so it's also a thing that go to infinity 0, and we have this plus n here. We'll shift this left and right on the k line. And so we plot our x of k on k, and our h of n minus k on k line, then we try to overlap them. Then we see that we do this in different order, but so we do this for n bigger than 0 first because it's easier. So we see that for n bigger or equal to 0, and this thing is the same thing, because h of n minus k will start from n, which is bigger than 0, and it will be 1, 1, 1, all the way to all the negative. So when you multiply this with x of k, you see that it's just x of k, because it's 1 because h of n minus k is 1 everywhere where x of k has value. Okay, so this is x of k, and this is summation of this geometric series, and it's a very easy one. It gives you 2. Okay, and then the harder one. So when your n is negative, then when you multiply your h of n minus k with your x of k, so some of your x of k is getting cut off. So here, like the 0 and the -1 get cut off. You multiply together, you start summing your geometric series with from 2 to the negative n, and 2 to the positive n, because n is negative. And yeah. So anyway, so here, for example, is n equal -2. You have summation 1 over 4, 1 over 8, 1 over 16, etc. And you do the formula, you see the answer is 2 to n plus 1. Okay. So this is actually easier example, although it goes to more infinite. But now we only have 2 intervals. Okay, so question about discrete time convolution. Otherwise, let's go to continuous time convolution. Okay, so continuous time convolution, we basically try to do the same thing as discrete time convolution, but now everything is a little fuzzy because now we need to deal with our delta function and things. So we will try to argue, hopefully that's convincing, that everything we do with discrete time can be also done in continuous time, by replacing the unit impulse in discrete time to the delta function in continuous time. And anyway, so this is our argument. We do this triangle thing. So we say, so whatever x function here, we try to replace it with a lot of rectangulars. So we cut the time interval into a lot of delta. So we have this 0 to delta interval and delta to delta interval, and maybe at some point we have k delta to k delta plus 1 interval. And we say between those intervals we approximate our function value as a constant, because hopefully the function is kind of smooth. So as we cut the interval smaller and smaller, if we approximate the function of these steps, it will be the same function. Okay. And if you do that, then our function will, just like a discrete time case, look like a summation of a whole bunch of those triangles shifted to the k delta. So remember, we have this delta of triangle that is height 1 over delta, and only has value between 0 and the delta. And okay, so we have those things, and because this has a 1 over delta here, so we multiply by another small delta here, so this delta will cancel this 1 delta. So this is just, so these two things together, oh, that sucks. Okay. So maybe it's still using pointer. So, yeah. So those two things together, this delta of triangle and this triangle, these two things together is 1 between 0 and the delta. Then it shifted to k delta. So it's a 1 at this place. Then you multiply them with the height of x at k delta. So this thing, so one of those terms will be a triangle on k delta. A rectangular on k delta here, like this. Then you sum k from 0 minus infinity to infinity. So you are summing this function with a bunch of those rectangulars. So you can see those from k to -2, k to -1, k to 0, k to 1, etc. So you try to approximate x with all those rectangular, and we think that you take small delta to 0, that will be the same thing as this function. Okay. And now what if we try to see what happened to this whole thing if we take a small delta to 0. And so another way, and we want to say the summation go to an integral when small delta goes to 0. And how does that make sense? That makes sense by saying, so now this, sorry, not small delta, so this triangle, actually big delta. So this triangle, as it goes to 0, it becomes like d tau, right? So we say this integral line, we call it tau. Okay. So that's an infinitesimal change in tau, so that goes to d tau makes sense. And this delta of triangle as it goes to 0. Okay, so without the k delta shift, then let's go to the delta function, because that's how we define delta function. It is one of the triangles in between 0 and the triangle. Okay. That's the delta function, and we have this shift of k delta. Sorry, k big delta, and the k big delta is we just call it tau. Okay. So it's whatever the place our tau is, and k delta goes to tau, so x of k delta goes to x of tau. Then the summation becomes integral. Okay. So hopefully you buy that, but even if you don't buy that, you need to remember this equation. So this is the continuous time convolution. So, okay, sorry, not quite convolution yet. It is another way to characterize delta function. Okay, so that's very useful, and I guess it's another way to see our shifting property. But anyway, so we can check this equation being correct by shifting another thing. So if we try to replace our x with u of t, so then that will give us you will see that u of t equal to this. So the inside u of t will cut off this minus infinity to 0. And we have u of t equal to 0 to infinity delta of t minus tau d tau. And that's one of the properties we show when we talk about continuous time impulse function. Okay, so that's a little digression, but that's back to our unit impulse. Okay, so I think this makes sense. Okay, so actually this is more important. I got it a bit wrong. So we should be looking at this function, right? So this is how we decompose our x into a linear combination of like something like delta, and we go to the same reasoning as a discrete time. So x is a linear combination of those delta of triangle. Then y should be going to the same linear combination, but with the response to those delta of triangle. So we use linearity. So x is a linear combination of a whole bunch of things. Then y is a linear combination of the corresponding responses. So this delta of triangle should go to h of k triangle, h sub k triangle. Okay. And then we take a limit of delta go to 0. Then now we do the similar thing that we argue. So as triangle goes to 0, so the triangle should become d tau, and k delta is whatever tau. Okay, and yeah, so k delta become tau, k delta become tau, and we have h of t equal to h of t. Yeah. Okay, so we are missing. Oh, never mind. Yeah. Yeah. So tau equal to k triangle, and summation become integral. And finally, we do the same thing. So we say the system is time invariant. So those h of tau equal to h0 of t minus tau, and h0 we call h. So now this is the continuous time convolution. So y of t equal to integral minus infinity to infinity, x of tau and h of t minus tau d tau. Okay. And remember this, everything is so remember this arrow represent our system. So we have x is input will map to y as output, and delta as input will map to h as output. Delta of t as input will make to h of t as output. And yeah, so we kind of hand wavy and using this triangle notation to derive our convolution here. But this convolution formula is the thing we'll keep doing. So just like discrete time, our LTI system will be described by this h of t. And so whenever you want to calculate y of t, you can just do this integral. This integral from minus infinity to infinity, x of tau, h of t minus tau d tau. And once again, you need to be careful about your t and tau. Remember, tau is the thing you need to integrate over here. And whatever you do, you should let it with some function with t. So tau should disappear after you do the integral. And don't mix t and tau together. Okay. Yeah. And once again, h of t is the unit-impulsive response, because it's a response to the unit impulse function, which is the delta function. No. Okay. Any question about the derivation? Is a little hand wavy infinitesimal analysis by calculus. But I think this is actually quite rigorous here. Just our derivation is a little funny with all those triangles. But the bottom line is you need to remember this formula. And you see it's very similar to the discrete time case formula. So discrete time we have summation sk h of t minus k. And you are just changing summation to integral, and k become tau and n become t. Okay. And if there is no question, then let's see the example. And so in continuous time, we basically don't see the first view. So remember when we say we see the convolution in discrete time, we kind of have a two view, and we say we look at the second view. And yeah, for continuous time, we are just focusing on the second view because it's easier to visualize and easier to calculate. So second view is we try to plot this x of tau and h of t minus tau on this tau line. Okay, so that should be what's highlighter? Maybe h? No. Anyway, yeah. So the taus are important here. Okay, remember we are plotting against tau. Don't mix tau and t with each other. And anyway, we plot x of tau and h of t minus tau. So our example here, we plot first example we plot the x of tau first. So h of t equal to u of t. So h of t look like this, and x of t once again we like our exponential because they are easy to integrate. So exponential e to the minus at, so decaying exponential, then times is u of t, so it's cut off t equals 0. Okay, and we change to x of tau, then the x of tau just look like x of t, except it's tau here. Then we need to have our h of t minus tau. So it's very similar to discrete time. We do the time reversal first. So we flip this left and right, so it should become something like this. And you will move left and right depending on how much. You will move left and right depending on how much t it is. Okay. So for positive t, we'll pull to here, and for negative t, we'll push to the left. And so yeah, So very similar to discrete time, except instead of summation, we now have integral. So for t less than 0, we see that the h of t minus tau is all less than 0, and your x of tau only have tau bigger than 0 part. So those two things has no overlap. And so when you multiply together, they become 0, and the integration over tau will be 0. And for t bigger than 0, then your x of tau is still here, and h of t minus tau now pull to the right. So we have some overlap on this region. Okay, and h of t minus tau is just 1, so it will just cut off h of tau to t. Okay, so we are just integrating this x of tau from 0 to t, and it's an integration over the exponential also. I will not say the detail, and you can do the integration. Hopefully you still remember your calculus, and exponential go to another exponential and some constant. That's the result. Okay. Okay. And yeah, so if we plot everything together, our result, then we see that for t less than 0 or y of t is 0, then t bigger than 0, we have this constant minus the exponential actually. So it's actually an exponential saturating to 1 minus a, like this. Okay. So this is all y of t. So any question about continuous time convolution? So it's very, so I guess recap. It's very similar to discrete time convolution, but instead of summation, we have integral. And let's just say this once again. Y of t is x of t star h of t, and equal to integration minus infinity to infinity x of tau h of t minus tau d tau. And when you do the calculation of this, so you want to plot x of tau and h of t minus tau on those tau line. So x of tau will just be whatever given with x of t, but with t replaced with tau. And h of t minus tau will be, you need to do time reversal on h first, and then you move it through this tau line by the time shift t. So depending on different t, will pull this from left to right. And then you need to see how much overlap this h of t minus tau and x of tau has. Then you see the overlap region, and you do the integral. And here, both of them all have one boundary, so it's easy to analyze the overlap. But obviously, we'll have a more complicated example in homework and test, where both of them has multiple boundary, and you need to be careful to see a different case of t and how your h of t minus tau and the x of tau overlap with each other, and do the integral carefully. Okay. So that's you will get more familiar in your homework. Okay. And if there's no question, then let's go to next part. We'll talk about property of LTI system, and we will analyze them by this h. So remember, we say a lot about this h of n or h of tau, h of n or h of t. We say that every LTI system can be described by values h. And we will describe all the property we'll talk about this chapter in terms of this h. So it's memory and invariability, causality, and stability. But before that, we will talk about some property about the convolution first. So actually, convolution has three properties: it's commutative, distributive, and associative. Basically means that the convolution is like a multiplication. So that justifies the notation here, because so this looks like a lot like a multiplication, right? It looks like x times h, and then we'll see that actually satisfy the multiplication-like properties. But before that, let's do a little digression here, and So something we want to stress is that we say our LTI systems are characterized by this H. So any LTI system can be totally described by this H, which is the unit impulse response. And so for discrete system, you can calculate the output Y as is summation, convolution, and for continuous time Y, you can calculate it by this integration convolution. But actually, if your system is not a LTI, then some LTI system can have the same H, but it's a different system. Okay, so you need to be a little careful. Make sure your system is LTI to do this convolution. So here is the example. So we have a very easy impulse response here. So let's say impulse response being h of n equal to 1 only n equal to 0 or 1. Okay. And so if the system is LTI, then you can calculate your y of n. So you have your x of n convoluted with this h of n. And with some calculation, you see that y of n is x of n plus x of minus 1. But there are also systems that have the same h, but are not LTI and they are different systems. So for example, you can have your y of n equal to this x of n plus x of n plus 1, and you square it. Now, because you have this square here, then this is not linear. So this is not LTI system. But if you put unit impulse to this y, you will get the same output response. And similarly, you have an even weirder system. So y of n equal to max of xn minus 1. And so you see if you input x is only 1 at n equals 0, then y of 0 will take this x of n and it will be 1, and y of 1 will look at this x of 1 minus 1 is also 1, and all other y will be 0. And so anyway, that's something to be careful about. And let's go to the properties that we say we want to say. So those are properties of the convolution. So first is that it's commutative, and it's true for both discrete time and continuous time. So just like we say, so it's like a commutative property for multiplication. So x of n star h of n will be same as h of n star x of n is for whatever x and h. Okay, and the proof is not too interesting, so you can just go home and check. So you just write down the formula and then do a change of variable. So say you define n minus k to basically k. So let's say n minus k equal to k prime, and you change things around, and you change k prime to k. And so you can check the math that it works. And similarly, it's also true for continuous time. So continuous time, you also do change your variable and move things around, and you see that it's the same integral. Okay, so that's very useful. And the second property is distributive property. So once again, it's like multiplication. For discrete time, is x of n and convoluted with h1 plus h2. That will be same as x convoluted with h1 plus x convoluted h2. And similarly for continuous time. And there are several ways to prove this. So first is you can once again brute force this with the definition, and you see the summation or integration is very linear. So you have h1 plus h2 here, then this multiplication with x is distributive, the summation is distributive, so everything works out. Or there is a little smarter way, is you use the commutative property to prove distributive property. So you see that you have, let's see, pen, So because you know our system is linear, so x1 star, sorry, wrong. yeah, eraser pen. So the system is linear, so you know x1 plus x2 convoluted with h should equal to x1 convoluted h plus x2 convoluted with h. This is by linearity, right? Because our system is linear. So input is x1 plus x2, the output should be the linear combination. And then by commutative, then you can swap around and you just rename things. So h convoluted with x1 plus x2 equal to h convoluted with x1 plus h convoluted with x2. Yeah. So that's more smart way to see this. But anyway, distributive property is true. And that means that if you have two systems, so if you have this parallel connection on your system, so your input go to some H1, they go to some H2, and then together, then last thing as you put your system through a system that has H1 plus H2. Okay? So, and something implicit is now we will. Okay, so this is a little confusing, but most of the time we will assume this interconnection of block will assume most of them are LTI, and we just write the H to describe what the system do. Okay, so it's a little ambiguous because we didn't really mark that it's LTI, but from now on by default all the blocks are LTI unless sometimes we do different. Yeah, from now on most the blocks are basically if we don't specifically say they are LTI, and we'll just write the impulse response to describe who they are. Okay, and anyway, so because the distributive property, if we have this serial thing that we add together, then we can just combine them into one block. Okay, and here's some example that we don't actually go through the detail, but say our x has some part, so some exponential decaying part to negative. The exponential decaying part to positive. So 1 have 2 to the n u of n, and plus another part that decaying to negative, that is 2 to the n. 2 to the n u of negative n, and have some h equal to u of n, and we want to calculate the output now because x has 2 parts. Okay, so this actually we can just do with linearity, but whatever. But anyway, so y of n is x of n convoluted with h of n, and yeah, and because x is summation of 2 parts, so y will just be a summation of the corresponding 2 parts. So it will be a summation of convolution of the first part and the convolution of the second part. Okay. And we skip the part where we do all the convolution. I think we have seen both of them actually. Yeah. So both of them we have seen in previous examples. And then you need to analyze the overlap between h and x. And anyway, here's the plot of the result. Okay. So something that saturates to 4 and something that decays to 0. Okay. And lastly, we have our associative property. And yeah, not much to say here. It's like an associative property with multiplication. So you have this x convoluted with h1 convoluted with. So you have h1 convoluted with h2 first, then you convolute it with x, the same as x convoluted with h1, then convoluted with h2. So the ordering doesn't matter when you do the convolution, and that's for discrete time, and the same for continuous time. And if you want the proof, you can try to do it in problem 2.43. But I think the proof is actually also very easy. Just take the definition and write down things. Then you manipulate the ordering summation and change some variable, and it should work out. Okay, so the proof is not too enlightening, but the result is very nice because that shows that the star symbol is just like multiplication, and because it has associative, so ordering doesn't change, so you don't need any parentheses. You can just write this as convoluted with h1, convoluted h2, and this is well defined. Okay? And similarly, in our block notation means that if we have the serial interconnection of our system, so first one with h1 and the second one with h2, then that's same as the system with h1 convoluted with h2. Okay? So yeah. So now convolution has more meaning. We can even convolute two systems. Okay? So I guess this is where people get confusing. So yeah. So now we have a function that represents a system. So keep saying systems and signals are different, but for your TI system, they are kind of the same, because the system is also defined by every system is also defined by a function, and yeah. So we can even do convolution between systems by doing convolution on their unit impulse. Okay. But yeah, so even though there is a one-to-one correspondence between the system and the unit impulse function, you still need to remember that the system is something that takes an input signal to an output signal. Okay. So don't get too confused between this correspondence. Okay. And yeah, so this is very nice. So we can do a lot of manipulation here. So for example, we see that you go to first system H1 and second system H2, then you see that same as going through a system as H1 convoluted H2. Then because we also have the commutative property, so we know H1 convoluted with H2 is same as H2 convoluted with H1. Then we see that same as you apply H2 first and apply H1 first. Commute, because their unit impulse function commute convolution. Okay. And yeah, we have 1 more minute, but I think we go through what we want to go through. So any question? Otherwise, we'll start with more properties on Friday. Okay? No question? Then let's stop today.